Hello all, welcome back. We got a pretty fun one to deal with, so I'm just going to go ahead and dive into it. We're asked, in a certain inertial frame S, the electric field E and the magnetic field B are neither parallel nor perpendicular at a particular space-time point. Show that in a different inertial system S bar, moving relative to S with velocity v given by v over 1 plus v squared divided by c squared is equal to E cross B divided by b squared plus E squared over c squared. The fields E bar and B bar are parallel at that point. Is there a frame in which the two are perpendicular? Okay, quite a bit to do with, and now we're just going to have to see that we're going to have to try to take advantage of the field transformation equations and see what else we can conclude about what we know from the transformations. All right, so what we need to do, of course, in defining everything is, well, same way we define frames, we need to define all the parameters here for this question. So choose axes so that E points in the z direction and B in the YZ plane. Again, neither parallel nor perpendicular, so we have to be somewhat in both. So we see that we have 0, 0, E, and then 0, B cosine phi, B sine phi. So go to a frame moving at speed v in the x direction. Okay, well, if that's the case, we see that our transformation rules give us this. So we have E bar, B bar with the appropriate transformation rules applied to it. And so we're saying that provided that we are parallel in the S bar frame, the ratio of EY bar over BY bar is equal to the ratio of EZ bar over BZ bar. So set the two ratios equal, and we can kind of start to compare. What we see here is that we had a gamma canceling in both ratios, fine. But what happens when we cross multiply over to kind of simplify? Okay, this leads us to a VB sine phi times B sine phi. And then we have this denominator, which is a lot to deal with. It's two terms. With this numerator, a lot to deal with. That's two terms. So we're going to have to FOIL that. And that's what we see on the next side. So that being said, we condense the left-hand side. So we get VB squared sine squared, and then we distribute everything else. What we see is that the purples actually cancel. A nice little coincidence there. We kind of like to see that. And by cancel, we see that they have a sine squared and a cosine squared. So Pythagorean identity gives us a 1 there. So not a cancel that goes to 0. But it shows us that we can simplify this down. As you can kind of see here, the 1 plus v squared over c squared comes from what we saw with the combining of those two, factoring out the cosine phi. That being said, if we move that to the left-hand side and we simplify everything else down, we have a v here in the purple and a v here on the e. So we get v times e squared over c squared plus b squared. So you can see we're kind of taking shape of what we need to be. That being said, if I divide over this parentheses over to the EB side of the cosine, and I divide over this parentheses to the V side, we can kind of start seeing that we're manipulating down exactly to what we need to be. That being said, now if we compare this to the cross product of E and B of the untransformed fields, you see that we get negative EB cosine phi. Okay, that's just the direct evaluation of the cross product. So if that's the case, we see that we can turn this numerator here and rewrite it in terms of E cross B. And if we turn this back into the vectorization, we have E cross B vectors. And so this little v here needs to be rewritten as a vector as well, because we know that E cross B is a vector. So what this is really showing here is a nice way to see that the invariance is coming through. So that's pretty cool to me. What a wild result to see, but that's pretty cool. So what we need to write formally is that no, there can be no frame in which E is perpendicular to B for E dot B is invariance. So the whole point of that is that if we were completely perpendicular, then the dot product would be 0. And that wouldn't work if we have the fields established in one frame and not the other. Because we showed earlier that the transformation of the invariant product, well, it's invariant for a reason. So that would negate what we proved earlier. So no, we can't. And since it is not 0 in S, it cannot be 0 in S bar. That's the main thing. If it was 0 in S, then we could probably see that it might be 0 in S bar, or find something that would make it 0. But due to the invariance, we know that it can't be there. So that is a wild result. A little more algebraic manipulation, of course, but we always go back to those invariant rules because they save us a lot of tedious headaches when dealing with some of these seemingly random questions on what exactly is allowable. So that being said, invariance for the win in this situation. And as you saw with conservation, invariance is starting to peek its head through and it giving us another tool to use. So cool stuff. We got more coming, so stay put.